Hi everyone. So in this video we're going to cover the topics meant for week 5. Okay, and the learning outcome is to solve problems using fluid mechanics principles. So you can count on this topic to be in your upcoming tests. Okay, so the complete topics for this week includes first is one-dimensional isentropic flow. Okay, so this is a continuation from the previous week where you learned about compressible flows. Okay, compressible flows meaning flows involving gases. And then next, we're going to look at the property relation for isentropic flow of ideal gases. What are the relations between the properties when we have such flows? And next is something called the critical properties. I'll be breaking this topic into several videos, 2 or 3, so make sure you watch all of them. Okay, so 1D isentropic flow. So one-dimensional flows can be categorized as what you see in this diagram here. Okay, what it means is basically the properties do not change in the y and z direction. It only changes in the x direction. Okay, x direction, for example, you can see here at the inlet we have A1, V1 and rho 1, and at the outlet A2, V2 and rho 2. So these values might be changing at point 1 and point 2, but it's assumed to be constant in the other two dimensions. So for example, we can have a normal pipe flow, okay, or here you have a list of other devices that could be categorized as a 1D flow, such as nozzles, diffusers, turbine blade passages. Flow quantities vary primarily in the flow direction only. Okay, so yes, it is an assumption, but it's an assumption that we can make with good accuracy. Okay, and then isentropic. We learned about this also already in the previous topic. Okay, isentropic means constant entropy. This is related to the stagnation properties, which if you have forgotten, I suggest that you go back to that video. Okay, now to understand this flow, let's go through this example. Okay, we have a gas flow through a converging, diverging duct. So far you have seen a converging flow where the flow or the profile of the system is something like this. Okay, it gets smaller, and a diverging, of course, is the opposite, like nozzles and diffusers. But what if you have a device that is both converging and diverging? Okay, so you're going to see that here. So this is the question. Carbon dioxide flows steadily through a varying cross-sectional area duct at a mass flow rate of 3 kilograms per second. The carbon dioxide enters the duct at a pressure of 1400 kPa and 200 degrees Celsius with low velocity. Okay, it expands in the nozzle to a pressure of 200 kPa. The duct is designed so that the flow can be approximated as isentropic. So we have all the information we need. We know that the duct has a varying cross-section area. The mass flow rate is constant at 3 kilograms per second. It enters at such pressure and temperature at low velocity. And what happens inside is it expands. And when gas expands, the pressure drops, okay, down to 200 kPa. And the flow is isentropic. All right. So what you have to find, determine the density, velocity, flow area, and Mach number at each location along the duct that corresponds to a pressure drop of 200 kPa. So what the question is asking is basically if the flow pressure drops from 1050 1400 kPa at a pressure drop of 200 until it reaches 200 kPa. So finally it's 200 kPa. But the drop, okay, the incremental drop, or I should say decreasing, would be 200 kPa at each step. So from 1400 to 1200 kPa first. And then 1800, 600, 400, and until you reach 200. Okay, so let's just do for one case, for 1200, the first pressure drop of 200 kPa. Okay, so from the property table, we know that we need this value, so you can go ahead and open table A2. You can find these values of the specific heat for CO2 and the gas constant, okay, R, and the specific heat ratio, K. Okay, so please pause the video if you want to verify that you can find these values. Okay, this is the diagram for this problem. So it is a duct that has a varying cross-sectional area. It's not a constant or, okay, something like that. This is a constant area. This is a decreasing area. But here it's varying. You can see that it starts big and then it becomes smaller like a nozzle. And after this point, at the pressure of 767 kPa, it starts to increase again. The area of the duct starts to increase. That's why it's called a converging, diverging duct. It converges at the first part, and there's this small part at the center. If you recall, this is called throat. And then it starts to increase again in its size. Okay, so this is the mass flow rate. It enters at 1400 kPa and 200 degrees Celsius. And this is the pressure variation that we get as the gas flows through the duct. Okay, the pressure starts at 1004, it drops to 200 at the exit. Okay, so we have to find a few properties, right? Let's just look at that again. We have to find the area, okay, density, Mach number, and velocity. All right. So how do we start? So first we note that the inlet temperature is nearly equal to the stagnation temperature because the inlet velocity is small. So remember, stagnation properties are related to properties of the flow when it is suddenly brought to a stop. Okay, that means at very, very low or zero velocity. So at the inlet, we can assume that the values are equal to the stagnation properties. Okay, so we have T0 or stagnation temperature equals to T1. And we have T1 is given as 200 degrees Celsius. Okay, so this is your T0, and then P0 is equals to P1 because the flow is isentropic and the stagnation temperature and pressure throughout the duct remains constant. We're talking about the stagnation pressure and temperature, not the static temperature and pressure. Yeah, so P0 is 1400 kPa. Now that we have these two values, we can bring our equation. We calculate the desired properties at the location where pressure is 1002. Why 1002? I mentioned just now. From 1004 to 200 kPa at a step of 200 kPa pressure drop each. Okay, so for that, we take the first one, which is 1004 minus 200, 1200 kPa. Okay, so from equation 2.5, so if you have forgotten this equation, you can re-watch or recap on the topics from the previous week. We learned about the stagnation properties and how to calculate. Okay, basically it's just using this formula. So from that we can get the temperature that corresponds to 1200 kPa as from this equation, T naught is 473. Pressure is, we take the pressure at which we want to find the temperature, so 1002 kPa, and the stagnation pressure is 1004 kPa. Of course, this is the specific heat ratio for CO2. Okay, put in the value of K, and then we get the final answer, 457 Kelvin. Okay, if you want, you can pause if you want to write it down, if you want to calculate it yourself. I really encourage you to do so. Okay, so with this value, we can find the velocity of the flow. That's the first thing we had to find. Velocity, this is from an equation that you have already seen and used. Also from the previous topic. Okay, 2 times the specific heat multiplied by the change or the pressure, the temperature difference. Okay, that's T naught minus T. We have this from before. And don't forget, when it's velocity, we always have to manipulate. We have to either times or divide by 1000. Okay, because otherwise this would give you a value that is 1000 times too small. So multiply by 1000. Then you get the answer as 164.5 meters per second. Okay, that's for velocity. Next is we can find the density of the flow at 1200 kPa. So if you recall, this is from PV equals to MRT. Density is mass over volume. Mass here, volume here. That would be equal to, you rearrange this, you get P over RT. Okay, density equals to P over RT. We have this, we have the gas constant, we have the temperature that we found the first thing just now, and we get the density of the gas. This is a very high density. Okay, it has been compressed. Next, we can find the area, the flow area. So this is just from the mass flow rate equation. Mass flow rate equals to rho AV. Rearrange for A, put in the values. This is density from the previous part, velocity from the first part. We get the area. Okay, that means at 1002, let's say somewhere here, this area is 13.1 square centimeters. Finally, the Mach number. Okay, so Mach number equation is V over C. We have V, of course. We need to find the C. Okay, the sonic speed. So that would be square root of KRT. Put in the values of K, R, and temperature. Again, don't forget your conversion. And you get 333.6 meters per second. Put it here, and we get the answer for Mach number. Okay, now that is for the first part, 1200. We had this temperature, velocity, density, sonic speed, area, Mach number. You have followed through all of this. So if you were to continue calculating for 1000 kPa, 800 down until 200, you get to complete this table like this. Okay, and there's 767 kPa. What is this? So this is given in the initial diagram. It corresponds to when Mach number is equal to 1. Okay, so it's equal to 1, if you recall, it's a sonic flow. Less than 1 is subsonic, more than 1 is supersonic. So this is the sonic flow. It is at this point. And it will correspond with the throat of the duct. Okay, that's the smallest part. Okay, so if you see this diagram, you can see how the pattern of the area and Mach number, and we have temperature, density, and velocity variation as it moves from the entrance of the duct at this part, okay, until the end at 200 kPa at this part. Okay, this is the plot based on the values in the table. So what can we observe from this example? The first thing is the flow area decreases with decreasing pressure down to a critical pressure value where the Mach number is unity. So there's a critical point. Okay, so before that critical point, the area of the flow decreases. You can see that here, obviously 13.1 down to 10, down to 9. And then somehow after that, it increases again. Flow area begins to increase with further reductions in pressure. So after 767, you reduce the pressure, but the area will increase. So that critical pressure value is 767. It corresponds to where Mach number is unity. This means Mach number equals to 1. Okay, the Mach number is unity at the location of the smallest flow area called the throat. Right, so I've explained this. Next, the velocity of the fluid keeps increasing after passing the throat, although the flow area increases rapidly in that region. So look at the velocity. It starts at 0 and then it keeps increasing. Okay, at the throat is 317, and after the throat, even though the duct becomes bigger, the velocity still increases. So it does not, the second part of the duct, okay, even though it increases in area, it does not behave like a typical diverging duct. Okay, because when you were looking at that, we were studying compressible fluid. This will slow down the flow. But for compressible fluids like this gas, the CO2, we get such an effect. Okay, that's the whole point of this example, to show you the effect. So the velocity will keep increasing quite rapidly too. It actually reaches 530.9 meters per second. So this is due to the rapid decrease in fluid density. So if you look at density, it decreases all the way. Mass flow rate equals to rho AV. So when the velocity increases, this is related. Of course, area is influenced as well, but due to the compressibility, okay, we see that the density decreases. The flow area of the duct considered in this example first decreases and then increases. So this is fixed based on the shape. It decreases halfway and then it increases the rest of the way. So such ducts are called converging, diverging nozzles. So it does have a special name. Okay, these nozzles are used to accelerate gases to supersonic speeds. Okay, look at the Mach number. We are getting supersonic speeds, and they should not be confused with Venturi nozzles. You learn this in Fluid Mechanics 1, Chapter 5. Chapter 6. Okay, these are just normal converging nozzles. They are used for incompressible flow. So two different purposes. Okay, this one is used for compressible fluids. Okay, the first use of such a nozzle occurred in 1893 in a steam turbine designed by a Swedish engineer called de Laval. Okay, so therefore this type of nozzle, converging, diverging nozzles, are often called Laval nozzles, named after the engineer that first popularized the use of this device. Okay, so that's it for this video. Be sure that you watch the next video. We're going to learn a few more important parameters and the equations to find them. And then in the third video, we're going to go through some exercises.